This video is part of the Commercial Building Electrical Design series. We're still looking at power distribution design. We've been going through and looking at the different type of branch circuits, but now common to all branch circuits, we want to understand ground and what that means and how that affects the design of our branch circuits. So again, taking a quick look at where we are in the process. We've gone through delivery systems, materials. We've gone through the different types of branch circuits and how those work, and now we want to look at grounding. So we have examined and hopefully understand the process and sizing both the conductors, phase conductors that is, and the breakers protecting them for basically all types of loads, and that would include motor loads, continuous non-motor loads, and non-continuous non-motor loads. As mentioned in the previous lecture, even though we have these components correctly sized now, we're not quite done with what is needed to fully specify the circuits. We will now examine the concept of ground connections in relation to circuits. First thing we need to understand in regard to this subject is to clarify some definitions. In the National Electrical Code and electrical building design, there is a very big difference between a grounding conductor and a grounded conductor. A grounding conductor is a conductor that is used to connect equipment or the grounded circuit of a wire system to a grounding electrode or electrodes. This is the green ground wire in a circuit normally referred to as the ground. A grounded conductor is a system or circuit conductor that is intentionally grounded. This is the white wire that is normally referred to as the neutral conductor. So the grounded conductor, which is referred to as a neutral, is only required for single-phase loads and multi-phase loads where there is a potential for unbalance in the loads on each phase. Neutrals are not required for three-phase motors, nor the supply side of step-down transformers, because in both of those cases we don't expect these loads to be unbalanced. Of course, a motor, of course, should be, if it's designed correctly, should be balanced. A transformer goes from a Y to a delta. The secondary side is Y, the primary side is delta, so that balances itself automatically, so there won't be any need for a neutral there. When they are needed, they are generally sized to the same size as the phase or supply conductors. There are some allowances where the conductor size can be reduced, but this is rare, so for all practical purposes, we size the neutral the same as the phase conductors in our work. When the load is balanced in a multi-phase system and there is a neutral presence, then there should theoretically be no current flowing in the neutral conductor. There is always current flowing in a neutral feeding a single-phase load, though. So these conductors connect to the neutral bus system, which is bonded to the grounding system at the service entrance only. So in the main service, you'll have a ground bus and you'll have a neutral bus, and you will connect those two, with a wire or some type of conductor there. In the panels downstream from that, the branch panels, you'll also have a ground bus and a neutral bus, but you are not allowed to connect those anywhere downstream. They can only be connected together, and they have to be connected together at the service entrance, so you can't connect it to any other place. So per the NEC, the neutral systems and the grounding systems may only be connected in that one place. So very important thing to remember. So the grounding conductor, which we refer to commonly as the ground, is always required regardless of the circuit or load type. This conductor is sized according to one of two tables in the National Electrical Code, depending on whether the ground is a part of the service entrance or a separately derived system like a step-down transformer, or whether it is a part of a branch or feeder circuit. Under normal circumstances, there should never be any current flow in the grounding conductor. If there is current flow in this conductor, then there is some type of fault condition somewhere in the circuit. So if the grounding conductor is to be a part of a service entrance, or if it's on a separately derived system like the secondary side of a transformer or from a generator, Then it is called the grounding electrode conductor and is sized in accordance with NEC table 250.66. And so here is table 250.66. And the way this table works is it's based on the size of the phase conductor. So we can either have copper or aluminum. So if we know our service size, so like for a 225 amp service, that we'd probably use 4/0, and so that would fall in this this row here. And so if we come across here, we'd see for the grounding electrode, that is the ground going out to the ground rod, that conductor size would need to be at least a minimum of number 2. The interesting thing here on this table, at least always has been for me, is once you get above this size conductor, or combination of, so if you parallel like 2 parallel 300s, 300 kc mil, then that would be 600 total. So you have to take the total cross-sectional area, you have to take the total area there. But once you get above this size, 3/0's the largest grounding electrode conductor you'd ever need. You don't have to use larger than that. So that's an interesting aspect there to think of. Now, many times we'll oversize that or continue to size it larger, but we're not required to by code. And some of that's because you don't really expect that much current flow in this conductor. I mean, if you have that much current flow for any length of time, then you've got a pretty big problem, and a breaker should trip by then. If the grounding conductor is to be a part of a branch or feeder circuit, then this grounding conductor is sized in accordance with table 250.122. And so here's this table here. So unlike the other table, this one's based on the breaker size that's feeding your circuit. So if you've got a circuit that's fed with a 100 amp breaker, you're going to need a number 8 ground. If it's fed with a 600 amp breaker, you're going to need a number 1, so on and so forth. So this one can go larger than 3/0. So this is what's always been curious to me. Our electrode is not going to be any larger than 3/0, but if we're grounding a piece of equipment, based on the breaker size, our ground will exceed 3/0. So these are the two tables. You need to understand the difference in the two tables and when you need to use each one. The other one's for service entrance. This one's for a branch circuit, feeding a piece of equipment. So I thought it'd be beneficial to look at some details that we commonly use in relation to ground. So here you have our main switchboard. So you see we specifically show the neutral and ground bus here, and we show them bonded together. This is the only place that they can be bonded together. And then from this ground, we usually make several connections. So the first is we'll usually drive a number of ground rods. In this case, they say 3/4 inch by 10 foot long copper clad ground rods driven 10 feet apart, and we'll see a detail for this on the next slide. And so we bond all those, and so the way these connections are usually made, you can use a ground nut, but more often than not, in my specifications, we'll say to do an exothermic weld, which is a CAD weld, and so that's where they put a little mold over it and run the wire through it, and then they put these chemicals in it, and it basically does an electrochemical weld. So it's like welding to them, because you don't want that connection to come loose, for sure. And so then we'll run this connection up to the ground bus. We also generally run a connection to the building steel. So we want the building steel, and this is for the protection of the occupants of the building. If for some reason an outside source were to energize the building, you would want to be able to dissipate that and have it not hold a charge. Plus, you do also get some grounding benefit from the footers. That's almost like additional ground rods. We typically do that. And then the other thing we do is if they're using metallic water pipe, we will ground that pipe. Again, it gives us some grounding benefit, but it also affords some protection in case somehow or some way those pipes were to become energized. So this is a pretty standard detail for the standard way we would install ground and the connections we would make to the ground for the incoming service. So as I mentioned, this is a detail of the ground rods. So we typically put a minimum of 3 ground rods on commercial work, especially larger work, and we put them in a triangle pattern. and we usually have them spaced at least the distance of the length of the rod. So you saw I specified 10-foot rods, so that's why they're 10 foot apart here. And so that's to help ensure that we have a good connection to ground. And we want those rods driven all the way into the earth, and then we CAD weld all three of them together, and then we take this connection into our service and connect to our ground bus. And we typically use PVC conduit, a non-metallic rigid conduit, which I think we talked about when we talked about that conduit. If you use metallic, especially if the lightning protection system, if there is a strike or a large dissipation of energy into our system, this can produce an inductor effect. And so, as you know, with an inductor, you can't change the value of the current instantaneously. It has to be gradually. We wouldn't want that in our grounding system, so therefore we use the PVC to help alleviate that, so that won't happen. So again, another typical grounding detail to show how we connect the ground rods. And of course, these will be somewhere right outside the building, near the side, probably just out from the footers. So you need to be sure and allow area and space for that, and then run that into your switchboard.